we talked about all the different things that we needed to start calculus, right? All the little preambles. Well, now we're starting it. So this is the limit of a function. So suppose f of x is defined when x is near the number a. And just so you know, if you go into any university course in calculus, which I'm thinking you are since you're here, they will throw out any actual math courses. They throw out theorems, corollaries, proofs, etc., etc. And so when you read them, they seem awfully overwhelming at first because the prof will read them quickly and then move on. But remember that they're just a way to express a concept for all the examples instead of just giving you one example that works and you learn it. A theorem is, hey, this works for every single example that looks like this. Okay? So here we have definition 1. Suppose f of x is defined when x is near the number a. This means that f is defined on some open interval that contains a except possibly a itself. Then we write the limit as x approaches a of f of x equals L, and say the limit of f of x as x approaches a equals L. So if you look here, what I want you guys to see is we do the limit as x approaches a. It's a little arrow. It's written right below the word limit. X approaches a. And then you have some function beside it. It might be f of x. It might be an actual function. It might be like x plus 3. It might be x cubed minus 7. It might be the square root of x minus 4. Right? It can be any type of function. Then there is some limit that it approaches. The catch is that the limit is not specifically what that value is at 4. So if we were finding f of 4 in the past, we would take 4, we would plug it in for our x, and we get an answer. And that would be f of 4. We agree? The limit is not what is x at 4. The limit is what is it approaching from the left and the right. So if from the left it's approaching 4, and from the right it's approaching 4, then the limit is 4. F of 4 might not even exist. It might be an open dot, but the limit exists. So what does that mean? So here it says, if we can make the values of f of x arbitrarily close to L, as close to L as we like, by taking x to be sufficiently close to A on either side of A, but not equal to A, you will see what a limit is. So let's look at this one. These are all functions. Do you see how there's 3 functions there? They're actually all 3 different functions. If you look closely, they're a little different, all 3 of them. This one is a continuous function, right? This one is not continuous, and instead of the dot being at AL, the dot, there's actually a dot down here. You see what that is? That graph actually has a dot right here. Okay? This one just has a point of discontinuity and no value at f of a. Okay? This one has a value at f of a. F of a is L. Do you see that? This one, f of a is actually whatever this is. Let's say it's h. F of a would be h. And then this one, f of a doesn't exist. It's an open dot. I actually don't care what f of a is if I'm asking for a limit. The limit is, from the left and right, what is it approaching? It's not what is f of a. So let's look here. From the left of a, I'm approaching what y value? L, correct? From the right of a, I'm approaching L. Do you see that? I don't actually care that this coordinate is at L. It's what is it approaching? So for this limit, I'd say the limit as x approaches a of f of x equals L. Because from the left and the right, they're both approaching a y value L. Okay? Now this one, from the left, I'm approaching what y value? L. From the right, I'm approaching what y value? L. So the limit as x approaches a of f of x of this function is also L. What about the last one? From the left, I'm approaching L. From the right, I'm approaching L. So the limit as x approaches a of f of x equals L. If you notice, f of a for all of those is different. Like f of a has a different value. We don't care what f of a is. We care what it's approaching from the left and the right. That's what a limit is. So for this one, f of a, if I just do function notation, f of a, so when x is a, y is L, right? For this one, f of a equals what? H. And for this one, f of a actually does, let's be a D, does not exist. Because it's just a point of discontinuity and there is no coordinate at A. But it doesn't affect our limit at all, because our limit is not what the value is at A, it's what's approaching from the left and the right. So let's use an example that isn't just L's and A's. So if I have determined the value of the limit as x approaches 1 of x minus 1 over x squared minus 1 using a table of values. Now, 1 is a problem for this function, because if I plug a 1 into the denominator of this function, what am I going to get? 0, right? So there's either an asymptote at 1 or a point of discontinuity at 1 or something is at 1, because if I plugged it back in, I would get an error in my denominator, right? We learned that in rationals. So we can use a table of values to discover this, because remember, I actually don't care what this value is. Do I care about 1 at all? No, I care as I approach from the left and get closer and closer to 1, and I approach from the right and get closer and closer to 1, what is my value? If I plug 1 in, 1 doesn't exist. It does not exist. But this does not affect my limit, because the limit isn't what the value is at 1, it's what is it getting closer and closer to 1 on one side and closer to 1 on the other side. So this is why I picked 0.9, 0.99, 0.99999. These should be flip-flopped. This should be here. Because 0.9999 is getting closer and closer to 1, correct? So if you can do this, because I have them put backwards, it should be like this. Same thing here as I'm getting closer. This isn't getting closer and closer to 1. This is getting further. So this should be 1.001, 1.01, and then this should be 1.1. I put them in the table upside down, because I want to get closer and closer to 1. Is 1.001 closer than 1.01? 1.001? Yeah, 1.00001 is even closer. I just hit my thumb on it. 0.99 is close to 1 from the left, right? 0.99, I'm getting really close to 1. 1.001, I'm getting really close to 1. Correct? So go to your calculator, and you're going to type in this function, x minus 1 over x squared minus 1. If you want your answers in decimals, which you do, you can't use the fraction button because it'll spit out your answers in fractions. So in your y1, I would technically put my numerator in brackets divided by my denominator in brackets so that I get decimal answers. So we go to our y equals, and we put in bracket x minus 1 divided by bracket x squared minus 1. And then we're trying to find the y value with those x's. Where do we find x values? We use sec or y values. We use second, trace, value, right? Now the key thing, the one thing that's great about the second trace value button is you don't have to do it every single time to get a new x. You can just input the new x. So I'm going to go second trace value, and I'm going to go 0.9 and hit enter. And I get 0.5263 ... right? Then I don't go second trace value again. I just type the next number and press enter. I can keep pressing new values each time. So now I go 0.99 and hit enter. I don't do second trace value. And here I get 0.5025 ... Then I put in 0.999. I'm getting closer and closer to 1 from the left. And I hit enter. And I get 0.50025. What do you think it's getting closer and closer to from the left? What y value do you think this is getting closer to? 0.5, right? So we can say the limit as x approaches 1. This is from the left, right? 0.99 is from the left. So we go from the left. From the left is just a little sideways line. That's how we say left. So the limit as x approaches 1 from the left of f of x. Actually, not f of x. There is no f of x here. Of this function. X minus 1 over x squared minus 1 equals 0.5. Right? That's from the left. So we're getting closer and closer to it from the left, 0.99999. That gets closer and closer from the left. Does that make sense? Now we're going to get closer and closer from the right. So we're going to put in 1.1 first. So I'm going to go 1.1, and I get 0 decimal, because it's further away, 476,190. And I put in 1.01, and I get 0 decimal 497512 ... And I get really close, 1.001, 0.49975, blah, 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 blah. Could I even put in like 1.00000000001? And it says 0.5. Right? I can make it even closer. The more zeros I add from the right, before I put a 1, I'm even closer to 1. But I'm still not at 1, right? I'm just really, really close. 1.000000000. I'm like so close to it that you actually probably can't visualize it, but I'm not at 1, right? So what's this one getting closer and closer to? 0.5 as well, correct? So now we're on the right side. So we do the limit as x approaches 1 from the right of x minus 1 over x squared minus 1. And I get 0 decimal 5. Now, if from the left and the right they're approaching the same value, which they are, then the limit as x approaches 1, without lefts and rights on it, is 0.5. They have to approach the same value. Because these are, from the left and the right, they're the same, I can say the limit as x approaches 1 of x minus 1 over x squared minus 1 equals 0.5. And that's how I can show the limit using a table of values. Yeah.
So when the function is just like this one has a point of discontinuity, will the limit always be like the y?
Yes,
Okay.
if it's a point of discontinuity. Yeah. Sometimes we're going to have like piecewise functions where this one will end up here and this one will end up down here, and then they'll have a left limit, right limit, but it won't be the same thing. But a point of discontinuity, yes, your limit will always be the y because it's what it's approaching, not what it is. Yeah. So that is showing with your calculator, with your table of values. Algebraically is often easier. Sometimes you can't show it algebraically, so you have to use a table. Or later on we're going to use L'Hopital's rule, but that uses derivatives, so we can't do it now. So we always try algebraically because algebraically is perfectly accurate. If you can do it algebraically, you get an actual answer. If you do tables, you're like, I think it's 0.5 because it's getting closer to it. But there's no actual accurate answer. So algebraically, how do we do it? So we go the limit as x approaches 1 of x minus 1 over x squared minus 1. So my issue currently is that if I plug a 1 in, I get a 0 in my denominator. We agree? So I can't just plug the 1 in. If I could plug the 1 in and I didn't get a 0 in my denominator, I could just plug it in and poof, I'd have an answer. But I can't do that currently. I can, however, factor the bottom. So I'm going to write an equal sign every single time because these are expressions and this step is equal to the next step is equal to the next step, right? We're using our equal signs correctly. So now my rewrite limit as x approaches 1 because I'm not filling it in. I write this limit as x approaches 1 every single step until I can substitute in the 1. Currently I can't because it would make a 0 denominator. I can, however, factor the denominator. So I get x minus 1 over, what is the denominator factor? Yeah.
X minus 1, x plus 1.
X minus 1, x plus 1. Which of these two factors is my issue? Which of these two factors, when I plug in a 1, creates a 0? X minus 1. If I can get x minus 1 to go away, can I plug in the 1 and life is good? Yeah, so I need to get it to go away. Wow, there's two that match. It's miraculous. Because at 1, what do we actually have on this graph? Two factors canceling off. A point of discontinuity. Okay? Because the factors cancel. So because these cancel off, I can cross them off. What is left in the numerator if the whole numerator cancels? A 1, and we have to write that. Is my issue gone now? When we did this in 30-1, we were actually just finding the y value of the point of discontinuity, right? After you canceled it off and you plug your x value in, you get your y, your point of discontinuity. That's what you were taught. It's a standard excellence question. So now I can plug the 1 in and I don't have a problem. 1 plus 1 is 2, not 0. Correct? So if I can substitute it in and it doesn't create a 0, I do. The moment I substitute it in, the word limit as x approaches 1 goes away. Because the limit as x approaches 1 is telling you, I need to plug this value in for x. The moment you plug that in, you don't have to write it anymore. So I'm going to plug 1 in for, substitute 1 in for x. So now I don't have to write that limit anymore. 1, 1 plus 1, and so I get a half. Which is the exact same answer, isn't it? This one is completely accurate. I algebraically did it. I got a half. The other one I went, I think it's getting closer to 0.5, right? What if we got closer to 0.51 and I messed up? So tables are helpful, but not completely perfectly accurate. All right. I did the decimals backwards again. All right. This one should be 0. So this one we have the limit. I'm going to do this. These aren't even, this isn't even getting closer to 0, so ignore these. That's not okay. Just do this. I'm going to get you guys to pick values because those are getting closer to 1, not 0. The limit as t approaches 0 on this one. You see it as t approaches 0? I copied and pasted the previous table and then forgot to change the numbers. So it's getting closer and closer to 0. Let's see if you can come up. People are okay with the tables if I give them the x's. If I don't give them the x's, they're like, meh, I don't know what to do. So let's look at a graph. You're not, but say this is 0. 0 is the limit where it's happening at, right? Do I actually care what the value is at 0? No. And in this case, if I plug in 0, what happens? I get an error, don't I? So at 0, it does not exist. I also don't care because I'm looking at limits. And limits, I don't actually care what that value is. I care from the left and the right. So if this is 0 on my number line, from the left, what is close to 0? Negative values. Do we agree? On the right, positive values. Yes? If I write 0 decimal, what would be close to 0? Negative. 0 decimal. Could I go 0, 0, 0, 0, 1? Is that really close to 0 from the left? What would be a little less close? 0 decimal, not as many zeros, right? 0, 0, 0, 1. And then this would be negative 0 decimal 0, 0, 1. What's the great thing about 0? You can do the exact same numbers positive on the other side and you're getting closer to 0 from the right. Correct? So I can go 0 decimal 0, 0, 0, 1, 0 decimal 0, 0, 0, 1. And I did the same thing, just need an extra one. And then this would be 0 decimal 0, 0, 1. So let's plug them in. So you type the original into your calculator. If you put it in a fraction, you will get decimal, or you will get fraction answers. So I'm going to put it in like this in brackets. So we do second trace value. Hopefully they're still drawing it. Negative 0.01, I get 0.1666. Negative 0.0001. 0.16667. 0 decimal 0 negative. Decimal 0, 0, 0, 0, 1. So is this perfectly knowledgeable exactly what it's going to be? Is that like, You can say, I think it's getting closer to 0.167, but we don't actually perfectly know, do we? When it's a table, and it's a weird decimal. It's a little hard, isn't it? So let's try it algebraically. We have the limit as t goes to 0 of the square root of t squared plus 9 minus 3 all over t squared. My issue is the t squared, correct? If I can get that t squared to cancel off, can I plug in 0? Yes, currently I can't, because if I plug in 0, I'm going to get 0 in my denominator. What did we practice doing? What's the only thing we could do now, maybe? Multiply by the? Nope, close. Conjugate. So conjugate is same two terms, opposite sign, right? Same two terms, opposite sign, because it gets rid of those radicals. It rationalizes it. And what we talked about was, when we multiply by the conjugate, where's the black? When we multiply by the conjugate, remember the ones that are conjugates we multiply together. The ones that are not conjugates we leave separate, correct? Because my goal is this t squared needs to get canceled off. If I embed it into that conjugate, it's going to be really hard to cancel it, isn't it? So we always multiply the conjugates, and the ones that are not conjugates we leave separate. Okay, so let's see what we get. We get an equal sign. Please, everyone, check and make sure you have equal signs running down the left-hand side, because these are expressions. Each one is equal to the next one. Then we get the limit as t goes to 0. Now, square root t plus 9 times square root t plus 9. What happens when you multiply two square roots that are the same together? The root sign goes away, yeah. So we're going to get t squared plus 9. And then if we want to show our work, the outside would be 3 times root t squared plus 9 is plus 3 root t squared plus 9. And then minus 3 times it is minus 3 root t squared plus 9. And we know we use the conjugate if and only if these two middle terms cancel, because that is the point of using the conjugate. You'll get one positive and you'll get one negative, and they will completely cancel off, right? Your middle terms cancel. That's the reason why you use the conjugate. And then negative 3 times 3 is negative 9. All over t squared, we do not distribute. I want this to go away. The t squared is my problem. It needs to get out of my life, right? That is our goal. That is our goal the whole time. What is making us have problems that we can't plug in? And I need to get that to go away. And then I have square root t squared plus 9 plus 3. Up here, the 9 and the negative 9 cancel. What am I left with in the top? I'll show this step. So the limit is, and I keep writing the limit until I plug that 0 in, right? You rewrite that limit over and over and over until you plug that 0 in, because that's telling you what x is. The moment you plug it in, the limit goes away. So on the top, I have t squared in the numerator. And then in the denominator, I have t squared, square root t squared plus 9 plus 3. Can I get my issue to go away now? Will the t squared cancel off? Yes, this one cancels off with this one. What am I left in my numerator with? A 1. If I plug the 0 in, does it create a 0 in the denominator now? No, so am I allowed to substitute at this point? Yes, I got rid of the problem. I can substitute in the 0. The moment I substitute in the 0, what can I drop off? The limit word, right? The limit word can go away. So I'm going to be left with equal to 1 over, no limit, so I'm going to plug in 0. 0 squared plus 9 plus 3, which is 1 over square root of 9 plus 3, which is 6. And 1/6 is actually what this is getting closer and closer to. Type 1 divided by 6 in your calculator. 0.16666. Right? Make sense? So it's what we're getting closer and closer to on the left and right. It doesn't mean it's what the value is at that value. And we know it's not, because at 0, we actually have nothing. There is a gap in this graph at 0. Okay? We're going to flip over. So like I said, I want you to be over-prepared for calculus next year, not under-prepared for calculus next year. So I'm looking at it from every form that I could possibly give it to you. Now, here we have the limit as x approaches 0, and I gave you the graphs of sine x, and I gave you the graph of x. Can we agree? All right. If I do sine x divided by x, and this was f of x, and this was g of x, just like in 30-1, which is why we do division of functions, addition of functions, multiplication, all this, because you're preparing for calculus. Here's the moment we need it. You're like, why are we doing this? Right now. Here it is. Okay? If I wanted to find the value at 0, which actually doesn't affect my limit at all, let's find the value at 0. I would have to do f, which is actually the sine x graph, divided by g. So I would have to take their y values and divide them. What happens when I get 0 divided by 0? You get a... Does not exist, but what do you specifically get? Remember when your x values are the same, you divide them out, and they cross off? You get a point of discontinuity. So we would get ourselves like a little 0. Little open dot. Do I actually care about that value? No, I care as I get closer and closer and closer to it. Correct? So what we would be doing is we'd be dividing them out. We take this divided by this, this divided by this, this divided by this. If we started out here, way further away, we would go 0.8 divided by negative 0.8 divided by negative 1, which would be 0.8. It would be here. Right? If we pick this value in here, it would be this one divided by this one, which would end up being positive 1. So we can do it with a graph, or we can do it with a table, right? I want you guys to try it with the table, but I want you to see what the table is doing. It's dividing your two functions apart. So this would be your x, your y would be sine x divided by x, and we need to pick values closer and closer to 0. Do we need 0? Do we care about 0 when we're doing limits? No, we need values close to it. So I can go negative 0 decimal 0, 0, 0, 0, 1, remember? And I can go negative 0 decimal a little further away. And then I can go negative 0 decimal 0, 0, 1. And I can go positive 0 decimal 0, 0, 0, 1. This would be on the right. 0 decimal 0, 0, 0, 1, 0 decimal 0, 0, 1. So this is where it splits. This is on the left, and this is on the right. You see if you can maybe come up with the... Right. So when I type in negative 0.001, I get 0 decimal 9999999. And then I type in negative 0.001, and I just... And then I get... And then I get aggressively a lot of 9s. What's it getting closer and closer to? 1. So this equals 1. Like I said, do I care what it actually is at 0? Nope, I don't. As a limit, it doesn't actually ask you what it is at that value. It's what it is from the left and the right. What's it approaching? If we can get that wrapped around our heads that we actually don't care what the value is at 0 or at 1 or at 2. The limit is what is it happening on both sides of it. Then you're in a much better boat. Okay? And why do we care about limits? People are like, why can't I just know what value is on the one side or the other? Because if you know what's happening on both sides of that value, you'll be able to draw the graph. And in the most part, for the most part, so are you guys been able to punch stuff into your calculators and draw graphs? Calculus, Calc 1 at the very least, teaches you how to draw graphs using derivatives instead of using this device. It'll show you where there's intervals of increase, decrease by derivatives. It'll show you where the maximum mins are, where the points of inflection are, where concavity changes, all that stuff. In the past, we've been able to find, is the x-intercepts and y-intercepts. That's not a problem. We'll still use that knowledge. But we'll be able to actually give all the rest of the information to be able to draw a graph without our calculator. All right. So this is the Heaviside function. H is defined by this. It's a piecewise function. Fun fact, the function is named after an electrical engineer and can be used to describe an electrical current that is switched on at time t equals 0. So that's what he devised this equation to represent. So they want the limit as x approaches 0 of h of t. So let's sketch this graph to see what the heck even happens at 0. Okay? It's a piecewise function. So this says h of t equals 0 if t is less than 0. So there is a function, h of t equals 0. What is that? That's the same as y equals 0. What is that as a line? What is the y equals 0 line, actually? It's a fancy thing. It's an axis of some sort. It's the x-axis. Y equals 0 is the x-axis. Because where is y equal to 0? On the x-axis, right? So what is this saying? It's saying there's a line. Do not draw this unless you have a pencil. There is a line. Let's pick a different color. There's a line y equals 0 on this graph. Why did I tell you not to draw it? Where should I have stopped? At t is less than 0, correct? So some people are like, well, how the heck do I draw up to 0 but don't touch 0? What do? We've done this before. I go to 0, but I put an open dot. Exactly. So I stop at 0. I shouldn't have kept going. And I put an open dot. So that's the left-hand side of this graph. Correct? And then on the right-hand side, we have h of t equals 1 when t is greater than or equal to 0. What is h of t equals 1? What is y equals 1? It's a constant function, which is a horizontal line, when y is 1, right? The catch here is I don't draw it the whole way across. Where does it start at? 0, and is it a closed or open dot? Closed, because there is a... Why is it closed? There's an equal to sign. So I go, put a closed dot. And I have a horizontal line running this way. You agree? There is an issue. From the left and the right, is it approaching the same thing at 0? Nope. So, note to self. It's asking me for the limit as x approaches 0, correct? The only way I can do that is if I actually show the left and the right approach the same thing. So let's show that. So the limit as x approaches 0 from the left of h of t. So as I'm approaching 0 from the left, I'm coming from the left. See, look at this. What's my y? What am I getting closer and closer to? Circus? Nothing? 0. Yeah, there we go. It's getting closer and closer to 0. It actually is 0. Right? All right. It's like you guys eat lunch and then you have nothing left. It's like you're just tired. I did a circus song and I had nothing. Just sadness. So I had. All right. I don't know why it's switching colors in the middle, but it does what it wants. All right. What if I'm approaching from the right this time? I won't make any noise because that didn't do anything. There's just nothing. On the right, what am I approaching? Don't all answer at once. Stop talking. Yeah, that's that one. So the limit from the left, does it exist? Yeah, what is it? 0. Okay, cool. Limit from the right, does it exist? Yeah, what is it? Does the limit at 0 exist? No. If the two do not come to the same value, You can have a left-handed limit, you can have a right-handed limit, but that doesn't mean the limit itself exists. Okay? So you're going to always show that from the left it's 0, from the right it's 1. Therefore, which is that little 3 dots we do in mathematics, because it's a real thing. It's not made up. I'm not making something up here. Oh gosh, this marker. Okay, therefore, the limit as x approaches 0, not from the right, not from the left, 0 of h of t, which is what they asked us, does not exist. It's really weird E, but. Okay, so we can have a left-handed limit at one value, a right-handed limit at another value, but if they do not match, the limit doesn't exist. Does that make sense? Because the limit is saying that from both sides we come to the same thing. And we don't in this one. We come here and we come here. Right? So that limit doesn't exist. The left and rights do. Speaking of one-sided limits, here we are. So one-sided limits. In example 4, you notice that h of t approaches 0. As h of t approaches 0, t approaches 0 from the left and 1 from the right. We indicate this solution symbolically by saying what we did above. From the left, it's 0. From the right, it's 1. This symbol t approaches 0 from the left with a little negative after the 0 indicates that we consider only values of t that are less than 0 from the left. And then when it has the positive, it indicates that we look at values of t that are greater than 0 from the right. Okay? So, definition 2. Well, those definitions again. It summarizes what I just said. Yeah? Yeah. So the limit as x approaches a of f of x equals L, if and only if, and they'll use IFF, which represents if and only if, the limit as x approaches a from the left is f of x, and x approaches a of f of x from the right is L. And if these are both L, then this one is L. So you have to show from the left it approaches L and the right it approaches L, then at just A it's L. So that's what that definition is. Okay? So we're going to look at some graphs here. So the graph of function g is shown below. Determine the values, if they exist, of the limits below. Does the limit actually ask me what the value is at that number? Do I care what the value is at the number? No. Limit is approaching from the left, from the right. If they're the same, the limit exists. What does this one mean? 2 from the left. We agree? Do I care about any of the rest of the graph? Nope, just 2 from the left. So I'm going to take my little pen. I'm going to go close to 2 on the left and follow it. Here's 2. I'm going to go from the left. What's it approaching? What y value? 3. Done. From the left, it's approaching 3. We agree? What does this one mean? From the right. From the right is a graph, totally different graph, right? Correct? So from the right, what's it approaching? It's approaching the y value of 1. So I have a left-handed limit at 3. I have a right-handed limit at 1. Those are real. That is true. There's nothing wrong with that. What is the limit at 2? Marcus, your voice just came out of Kyle. It's the craziest thing. Yes, does not exist. All right. Yeah, that's crazy. Take that show on the road. All right. So, I want you to try the bottom one. 5 from the left, 5 from the right, 5. Go. This one is 5 from the what? 5 from the which direction? Left, which is? 2. Okay, so 5 from the left. As we approach from the left, we are approaching 2. Do I actually care about this dot, guys? Do I care about that dot? That dot is f of 5 equals whatever the heck that dot is. I just covered it up. Was it a 1 or higher? 1? Cool. I don't actually care about that, though, if I'm talking about limits, right? So from the left, it's approaching 2. From the right, it's approaching 2. So what is it at 5? 2, because they approach the same value. So if the limit exists, then that means I don't even have to talk about left and right. That just tells me that from the left and the right, they're both approaching 2. Correct? All right. So This one is the limit as x approaches 0 of 1 over x squared, if it exists. Cool. What about this? What's the answer to this? Does not exist. You guys try and see if you can figure out what those might be. What's happening as I'm getting closer and closer to 0, even if you just look at the graph on the right-hand side. This one is approaching what? Positive infinity. This one is approaching what? Positive infinity. Watch yourselves. Is positive infinity an actual value? Or is it a concept? It's a concept. We're approaching infinity. Infinity is not like a number. You can't say it is infinity. No. It is moving to infinity, towards infinity. There is no actual value for it. So what we can do is we can go the limit as x approaches 0 from the left of 1 over x squared. That limit, so as I'm approaching from the left, where am I going to? Positive infinity. Do I have to show the positive sign? No, I'm just being excessive. I don't know why I put positive. Okay? Then from the right, the limit, as x approaches 0 from the right of 1 over x squared. What am I approaching? Positive infinity, correct? The rule for a limit existing at a specific value, not from the right and left, is that it has to be the same number. Is infinity a number? No. So, the limit as x approaches 0 of 1 over x squared does not exist. Left-handed limit exists, so it tells you that it's approaching infinity. The right-handed limit exists, tells you it's approaching infinity, but they're not actually approaching even the same infinity. One's on one side, one's on the other, and there's an asymptote occurring in the middle. Right? At that 0. All right. Try this out. See if you can do it. You're drawing 1 plus x less than this, x squared between those values. I would use a pencil. So if you're working on it, keep working on it, totally fine. I'm just going to talk to it. So if I have 1 plus x and it's less than negative 1, I'm going to start at negative 1 first. And I'm going to go 1 plus negative 1, and I'm going to get 0. And it's going to be an open dot because that's not equal to. Do you agree? Start negative 1 and 0, open dot. Then I can pick something else on the left of it. Negative 2. 1 minus plus negative 2 is negative 1. Now I'm at negative 2 and negative 1. And then the slope is 1 and 1, so it's going to be like this. And it has an arrow at the end because it says less than negative 1. It doesn't say to like a certain value. It doesn't stop. The next one is x squared. So now I would have x and then x squared. But it starts at negative 1 and goes to 1. So if I put negative 1 in here, negative 1 squared is 1, and it's a closed dot because it's equal to. So I'm at negative 1 and 1, closed dot. I plug in 0. I get 0 squared, which is 0. Then I plug in 1. 1 squared is 1. And it's closed. It's an open dot because it's not equal to. So we have this. Come on. And it's rounded because it is a quadratic. You know that it's rounded. You know what the graph of x squared looks like. Could I pick more values in between to make it more accurate? Could I pick like 0.5 and negative 0.5? Sketch those lines. It's more accurate? Absolutely. Okay. And then my last one is x. And 2 minus x, I'm going to start at 1. 2 minus 1 is 1. And then it is a closed dot because it's equal to. Make this one a blue graph. Wait, 1 and 1 is now filled in. That fill in trumps the open. So it actually fills it in. Okay? And then I pick 2. 2 minus 2 is 0. And then it's also negative 1 slope. So it's going to go this way. So this one is asking for what values of A does this graph have a limit? Does the limit at that value exist? Not from the left, not from the right, at that value. So, if I look at -1, does it exist? Does the limit as x approaches -1 exist? Let's talk about it. The limit as x approaches -1 from the left of f of x. What does it equal? As they're approaching from the left. Equals 0. That's what it's getting closer to. The limit as x approaches -1 from the right of f of x. What is it approaching? 1. Are they the same? No. So the limit as x approaches -1 of f of x is what? Does not exist. We agree? And what's the other point we're looking at? 1. x1, right? So we do the limit as x approaches 1 from the right of f of x. 1 from the right, it's approaching 1. The limit as x approaches 1 from the left of f of x. 1 from the left is 1. So the limit as x approaches 1 is what? 1, because it's the same. If I did 3, what would my limit be? From the left and the right, it would be approaching -1, correct? If I did 4, from the left and the right, it would be approaching -2. So those are all good. So where is actually the only place the limit doesn't exist? On that whole graph. The whole graph, the only place it doesn't exist is -1 because there's a gap. If at any point in time the graph isn't continuous and it gaps, from the left and the right approaches a different thing, that's where it's open. So this one says, sketch the graph of the function and use it to determine the values of a for which the limit is x of a of f of x exists. The limit as x approaches a of f of x exists everywhere but what? X approaching what? This is your homework.